Stanford University.
Okay, so we've talked about a lot of things so far. Fields, quanta of fields, the relationship between fields and particles. That's the relationship between fields and their quanta. What are the quanta? The quanta are the discrete, indivisible units of energy that quantum mechanics implies for waves. And waves, of course, are fields. Fields and waves are more or less the same thing. We've discussed the properties, not the properties of individual particles very much, but we've discussed some general properties, the properties of having energy, momentum, the properties of having spin, and the property of either being a fermion or a boson. Every particle is either a fermion or a boson. Fermions are the particles that don't like to live together in the same state. Bosons are the particles that do like to congregate and do condense into the same state. We've talked about wave equations on occasion, or the field equations, if you like, more generally, various kinds of field equations. And we talked about how field equations can be generated from Lagrangians, from action principles. The quantum mechanical version of the Lagrangian is a kind of tool for codifying, or codifying, whatever the right word is, codifying the interactions between particles. Various terms in the Lagrangian, things like, for example, products of fields, represent processes which we can call vertices, where particles come in and other particles go out. That would, for example, be a term in the Lagrangian which would have 4 powers of a field in it. So we've talked about these general things. We haven't talked very much about specific particles. Tonight, well, I expected to spend the first half hour beating around the bush a little bit. Looks like we're going to spend a few more minutes beating around the bush. But then I want to come to really writing down what the particles are, who are the players in the drama, and start going through them more or less, well, not quite one by one, but in groups, and trying to give them some personality, give them some names, some properties, and also what it is they do and how they come into physics, into ordinary physics. Okay, but before I do that, there's kind of a triangle of concepts that we've discussed 2 legs of, but not the third leg very much. The triangle is particles or field quanta, particles, fields, and in modern physics, pretty much for every elementary particle. Now, we're going to have to think very hard in the future, not tonight. What is an elementary particle and what is a composite particle? We will come back to that. And you might think, everybody here probably has some answer if I were to ask you, how do you distinguish a composite particle from an elementary particle? And you will always be frustrated. You will always find some slippery reason that your definition didn't work. But for the moment, let's nevertheless imagine that there are elementary particles, and that the elementary particles are the quanta of elementary fields, fundamental fields in the theory. And so they're more or less in one-to-one correspondence. But there's a third leg to this triangle. Anybody know what it is? Of course, you don't know what I'm thinking, so even if you did know what it was, you still wouldn't know it. Forces. 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 And in a certain sense, forces. Forces. Okay, basically, for every field, there is a particle. For every field, there is a force. Electric field gives rise to electric forces. Gravitational field gives rise to gravitational forces. It may be less obvious to you what the electron field. The electron has a field. It also gives rise to forces, and we'll talk about them a little bit. So there's kind of a correspondence that goes this way. There's a correspondence which goes this way. There must also be a correspondence which goes this way, a way of thinking about forces which is not based on fields, but which is based on particles, if this correspondence or this triangle really makes sense. So I want to talk about that a little bit. Many of you know the idea, but let's just discuss it for a moment. Let me first discuss it in the context of electrodynamics. How forces come out of thinking. Now, this is classical electrodynamics for the moment, the complete field view of things. Supposing I put two charges into space, and I want to know the force between them. How do I calculate it? Well, you could know the rule that the force is equal to the product of the charges times 1 over r squared and so forth. Or you could try to calculate it a different way. You could try to say, what do these two charges do to space? What they do to space is they create electric fields, right? Essentially, that's the thing they do. They create an electric field that fills space. And I don't want to write down the details of what that electric field is, but let's just say this is the electric field. Let's forget the second particle and just write down the electric field due to the first particle, whatever it is. The electric field due to the first particle. Incidentally, it's proportional to the electric charge of the first particle. So let's explicitly put that in. E of the first particle times the electric field divided by the electric charge. This electric field here, I've divided out the electric charge. Maybe I shouldn't call it E. Let's call it E without the factor of the electric charge in it and put a little hat over it. Right? That's this electric charge. And what is the field energy? Anybody know what the formula for the field energy is in an electric field? Electric fields have energy. They store their energy as a distribution of energy in space. And the field energy, the density of field energy, is the square of the electric field. Right? So we square this, and we integrate it over all space, d volume, and that's the energy stored in the electric field of the particle. Now, this energy does not depend on where we put the particle, right? The field will move. If we move the particle, the field will move with it, but the field energy will always be the same. Right? The electric field will adjust to the position of a charge. The field will always give rise to exactly the same field energy. And this field energy here, remember E equals mc squared, that field energy is part of the mass of the particle. It contributes, the field contributes to the energy of the particle, and therefore it contributes to the mass of the particle. There's another way of thinking about it, a bit of renormalization, that there's some extra mass there because the field surrounds the particle in this way. Okay, I don't want to belabor that now. What about the second particle? Supposing the first particle wasn't there, but the second particle was there. This, of course, is the energy, E. Not the electric field. This is the energy. If there was only particle 2, the field energy would be the integral of E2 times the electric field of the second particle squared. Now, if the two particles are not at the same place, well, let's not worry about the two particles. This one would also be independent of the position of this particle here. What about the energy if I have both particles? If I have both particles, then I have to add up the field first before squaring it. So the electric field, if I have two particles, will be the sum of the two electric fields. Electric field, not energy. Let's call this energy, En. H? Well, let's not call it H. Energy, just N. The energy, first of all, the electric field. The electric field will be the sum of the two electric fields. The electric field will be E1 plus E1 plus E2 E2. where these are the electric fields of particle 1 and particle 2. This will be the total electric field. Incidentally, the electric fields are vectors, and so we might put little vector signs above them. The field energy you get by squaring this whole thing. So the field energy is the integral over space. There are three terms. The first term is E1 squared, gotten by squaring this. The second term is plus E2 squared. And the third term is the interesting one. It's the product of E1, E2, twice as a matter of fact, times E1 dot E2. Actually, dot product. All right, what is this first term here? It's the self-energy of one particle by itself. It doesn't depend on the position of the particle. It's just a number. It's part of the mass of the particle. Let's forget it. It's already there as part of the mass of the particle. What about this one? Also, part of the self-energy of the second particle. What about this one here? This one is not the energy of either particle separately. It's proportional to the product of the charges, and it's proportional to the product of the fields. What if the particles were infinitely far away, so far away that their Coulomb fields hardly overlapped at all? You take one particle so far away that the Coulomb fields are hardly overlapping. Then this is going to be 0, because wherever E1 is not 0, E2 will be 0, or almost 0. Wherever E2 is non-zero, E1 will be close to 0. So this will be very, very small as you take the particles apart. But what about when you bring them together? When you bring them together, the product of E1 times E2 will not be small. Nearby, where the particles are, both fields will be appreciable, and you will get a contribution from this. What is that contribution? That contribution as a function of distance, well, first of all, it's proportional to the product of the charges. It depends on the distance. And of course, if you work it out, as you might expect, it's nothing but the Coulomb force, 1 over r squared. But I like to say it this way because it gives you the following picture, that putting in both charges, taking them far apart, they don't affect, well, they're simply just independent objects. As you bring them together, they deform and distort the field in a way that depends on the distance between them, and the distortions of the field in between them, that field energy, which is the contribution because both of them are there, that's the force law. So that's a purely field point of view of forces. A purely field point of view of forces. But if fields are nothing but collections of quanta, and quanta are particles, there must also be a way to think about forces in terms of particles. So let's talk about that a little bit. Before discussing electrodynamics in this way, let's talk about a slightly different setup, actually a very completely different setup. Let's talk about molecular forces. What do molecular forces come from? I'll give you one source of, there are several origins of molecular forces. But here's the setup I want to think about. Let's begin with a pair of protons and a single electron. Okay. What is this? A proton over here, a proton over here, and a single electron. If this proton were very far away, then the ground state of the electron in the presence of the proton would just be the hydrogen atom ground state. It would be governed by some sort of Schrodinger wave function. Let's draw the Schrodinger wave function. The ground state would be the ground state of the hydrogen atom. And in the ground state, if this proton weren't there at all, not there at all, the electron in its ground state would certainly be found in the position nearby this proton. Right? Now, what if there are two protons over here? One proton over here, another proton over here, pretty far away, but not infinitely far away. Then there is another possible state of the electron with exactly the same energy where the electron is not over here, but it's over here with the corresponding wave function pushed over to here. It has exactly the same energy. Why? Because the two protons are of the same kind, and everything is completely symmetric over here. So if the electron is in orbit, well, a quantum mechanical orbit around this proton, or if it's in quantum mechanical orbit around this proton, the ground state energy will be exactly the same as if there was only one proton. But it's not quite true. Why isn't it exactly true? Well, if the protons are not infinitely far away, there are processes that could happen which could not happen if they were infinitely far away. Anybody know what the process is that can happen to the electron if the two... The which?
I would guess the tunneling effect.
Tunneling effect. Yeah, the tunneling effect. The electron placed over here into its ground state can, with a small probability, suddenly appear in this atom over here. That's called quantum mechanical tunneling. It has to overcome an energy barrier in between the two. It takes some energy to pull the electron out of this atom. It'll get that energy back when it drops into this atom, but it has to go over this hill. Can it go over the hill? Classically, it can't, but quantum mechanically, it can tunnel from one place to another. Don't stand there and try to watch the tunneling. What happens if you try to watch for the electron going back and forth? Like anything else in quantum mechanics, watching it ruins it. You can watch over here. You can say, well, you can stand over here and wait for the electron to appear over here. But if you watch it from in here, you'll ruin the phenomenon. So the electron can hop back and forth. Hop back and forth simply means that there's a tunneling transition, a tunneling rate, or a tunneling probability that if you put it over here, it can appear over here. If it appears over here and you wait a while, it'll reappear over here, and so forth. Okay, this process sets up a kind of equilibrium, long-term equilibrium, in which the electron has an equal probability of being over here and over here, with a wave function which looks like the sum of the two wave functions. Well, the sum divided by the square root of 2 in order for probability to add up to 1. All right, so it looks like the sum of the two wave functions, which I didn't draw very well. But in the middle over here, it's slightly different. You might draw the exact wave function of the electron orbiting particle 1 as if particle 2 were not there. Same thing for particle 2. And then add them up. Well, the correct tunneling wave function, the correct equilibrium wave function is not exactly the sum of these two wave functions. It's a little bit different in here. A little bit, not much. But the point is the energy of the system is not exactly what it would be if the two protons were infinitely far away from each other. If they were infinitely far away from each other, you could put the electron over here, it would have a certain energy, or over here, and it would have exactly the same energy. When you put them closer together, the energy of the electron is not exactly the same as it would be if they were far apart, if they were infinitely far apart. So if I were to plot the energy, as a function of the distance between them, when they're very, very far apart, the energy of that electron is simply the energy of the electron with only one proton, and the other one just not there at all. At large distances, the energy would just be whatever it was. But as you bring the protons together, the energy of that two protons plus electron is a little bit less. Turns out to be a little bit less, and that little bit less is a function of the distance between them. So now we have a situation when the system is in equilibrium with the electron tunneling back and forth and in equilibrium between the two. The energy is a function of the distance between them. What's the relationship between force and energy? You can think of this as potential energy. You can think of this as a potential energy between the two protons. The derivative of the energy. So the derivative of the energy has a gradient in here. Force always pushes you toward decreased energy. And so this effectively creates an attraction between the two protons. That attraction is a kind of covalent bond. It's a kind of force between the two of them, which is due to the sharing of an electron, or to the fact that the electron can be in a superposition of quantum states in the two wells, in the two potentials of these two things here. Now, does that mean that a proton and another proton with an electron between them, which has this attractive force, will bind together? Not quite, because there's another force around. What's the other force around? The electrostatic force. The system doesn't have zero charge altogether, and so there's a repulsion force, and the repulsion force can overwhelm the attraction force, but nevertheless, there is a force between two protons if there is an electron around, which is due, in a sense, to the jumping back and forth of the electron, or to the diminishing of the energy by the wave function sort of adjusting a little bit better than it would if you just added the two wave functions together. As I said, that's the origin of covalent bonds, sharing of electrons. And in this case, you can think of it, you can draw a picture. Now, the picture may or may not do anything for you. You have a proton over here, that's the world line of a proton, another world line of a proton, and the electron might start out being bound to this proton, hop across to this proton, hop back across to this proton. You shouldn't take this too literally, because if you stood in the middle, as I said, you would disrupt the process. But it's a description of the quantum mechanical state of the electron in between the two protons. What it does, this possibility of the electron jumping back and forth, lowers the energy relative to if you just had one proton and just one electron in the bound state there. That means that there is an effective force, and you can picture it. This picture is is like any analogy. It's often very, very misleading. But the presence of the electron in between the two protons creates an attractive force. It's called particle exchange. It's called particle exchange or electron exchange between the two protons. Now, yeah.
Could you think of it as being the electrons hopping back and forth as reducing the effective positive charge of the?
No, I don't think that that is quite the right picture. It doesn't really depend on the electric charges. It just depends on the fact that you can find, by adding together two wave functions, you can find a wave function with a little bit lower energy than either one separately.
Is this what Feynman referred to as like, likes, like?
As what?
Feynman used to say like, likes, like.
Like, likes, like, I don't know. No. He was probably talking about the Bose statistics of that photons like to be in the same state. I don't know what he was talking about.
No, he made the statement that he said that like likes like electrons like each other, protons.
No, electrons hate each other. They don't like to be in the same state. Photons like each other. They love to be in the same state. I think he was probably talking about the opposite of the exclusion principle for photons, the Bose statistics of them. Of course, I don't know.
Protons have a tendency to repel.
Protons.
Protons.
Yeah, that's because of their electric charge.
Right. Now,
Yes.
what happens is when you put the electron between them, is that reducing the repulsive force?
It does a little bit, but not very much. And in fact, the force due to the electron jumping back and forth is a much shorter range force than the electrostatic attraction. So this force would only be important at relatively small distances, whereas the Coulomb force would fall off much more slowly. So the Coulomb force would be a longer range force. But, you know, it is there. It is there. The places where it shows up is if you have a neutral system. I mean, it shows up better if you have a neutral system. If you have 2 electrons so that the total charge of the system is 0, then, of course, you have the possibility 1 electron orbiting around this proton, a second electron orbiting around this proton here. Now, the 2 objects here, they're called atoms, hydrogen atoms. They're neutral. There is no electrostatic force between them. But you still have this possibility of electrons jumping across. Right? Electrons can jump across or tunnel across. And then it does create an attractive force which can bind an atom, bind a molecule.
But even so, unless I'm mistaken, H2 plus positively charged hydrogen is bound.
Yeah, it is bound. But yeah, at small distances. At small distances, it is enough to overcome the Coulomb force. That's right. Right. Yeah.
Is there a possibility that between the 2 protons it's creating some kind of tension between that creates some third force that the electrons kind of orbiting around?
Well, it doesn't create a third force, but it creates a sort of slightly nonlinear effect due to the 2 forces. But it's just a solution of the Schrodinger equation in the presence of the 2 forces does not have the energy that it would have if it was just one of those charges there. But let's leave it at that. There is this notion of the energy being lowered by the possibility of alternating between 2 quantum states.
Is this thing at all related to quantum entanglement? Because you have
Not so much quantum entanglement. It's related to what are called off-diagonal elements in the Hamiltonian, but which is, it's not too closely related to entanglement, I would say. For entanglement, normally you need 2 electrons. You only need 1 electron for this.
For very high temperatures, does the electron move between the protons with a much higher probability?
Well, at high temperatures, because it depends on the temperature. At very, very high temperatures, all that'll happen is the electron will get kicked out and go to Alpha Centauri. And it won't even remember the fact that there was a proton around if it gets hit hard enough by a very hot photon. But if the temperature is not that extreme, what it can do is cause, even if you only had a single atom, it could cause the electron to occupy higher levels. Now, higher levels have bigger wave functions. So the overlap between the higher wave functions could be larger, and it would certainly have some effect on the force. But that's a kind of special effect. All right, we have a concept that we see in the classical electrodynamics, that the effect of having 2 charges changes the energy in between relative to what it would have been if you only had 1, and it creates a force. Similar kind of thing here. If you have 2 force centers and the possibility of the electron being in a superposition of states, in other words, of the equilibrium being in a quantum superposition of the 2 states being over here or over here, that also lowers the energy and creates a force. Is there a way to think about the Coulomb force here in quantum mechanics where it is in some sense similar to this jumping back and forth of the electron? Yeah, there is. Let's come back to a single proton. A single proton is interacting with the electromagnetic field. That means it's interacting with the field whose quanta are photons. Classically, we might just describe it by solving the field equations for the electric field in the presence of a charged particle. Quantum mechanically, we think about it differently. Particularly in quantum field theory, we think about it as the emission and absorption of photons. All right? That's what the Lagrangian of electrodynamics tells us. It tells us about the probability for the emitting and absorption of photons. So one way of thinking about the electron is that the actual physical electron is a quantum mechanical superposition of states in which, first of all, there are no photons. A superposition of a state with no photons, a superposition of states in which a photon has been emitted, and therefore there's a photon present. So it's a charged particle together with a photon around. Two photons can be emitted. The photon can be reabsorbed. The net effect in the end is some kind of equilibrium distribution, quantum mechanical equilibrium distribution of photons surrounding the electron. And you can measure those photons. I mean, a little bit different than measuring free photons. These photons are sort of trapped at the electron. They're emitted and reabsorbed. And if I have another electron over here, it is also emitting and absorbing photons, so there's an equilibrium. Okay. But every so often, now this should be thought of in the language of Feynman diagrams, every so often a photon which is emitted from here gets absorbed over here. And I always think about it as two jugglers, each juggling balls, and every so often, if they happen to be close enough together, a mistake will be made, and Joe will grab Mo's juggling objects. Okay. Really, what you really want to do is you really want to calculate the energy due to the electromagnetic field or due to the quantum superposition of photons that are present. You want to calculate that energy as a function of the distance between the charged particles. When they're very far apart, the two energies just add. You just get the sum of the energy of one charged particle and another charged particle. But as they get closer together, the charges begin to influence each other, or in the language of Feynman diagrams, the emission of one photon by one particle and the absorption of that same photon by another particle creates a force, creates an energy which is not exactly the sum of the two energies. And that energy is the Coulomb force between the charged particles. So we have two distinct languages. Well, apart from just writing down the Coulomb force law, we have two other ways of thinking about forces. One of them is through classical field theory, where you calculate the fields of objects and square them. And the other way is through the exchange of particles. Feynman diagrams where particles are exchanged back and forth. Any particle can be exchanged in some context or another. So every kind of particle in one way or another produces a force. In molecular physics, it's the exchange of electrons which create forces. In electrodynamics, it's the exchange of photons back and forth which create forces. So any particle is also connected with a force when that particle can be exchanged or jump back and forth between something else. We'll describe some more examples, but I did want, before we move on, to just discuss the relationship between particles and forces. So we more or less have a one-to-one-to-one correspondence. Particles, fields for which those particles are the quanta, and forces which are associated with exchange processes where that particular kind of particle can bounce or jump back and forth. That's an important theme. So when people say that there are four forces in nature, no, there's a force for every possible kind of particle. And we will discuss some of them as we go along. Okay, I think it's time now to start naming the particles, listing them, listing their properties, and discussing what they can do, what kind of processes they can engage in. And I could write down a big, long list of all the elementary particles and then give you a test next week to see whether you memorized it or not. That wouldn't be fun at all. I think it's probably better to divide them up into small groups, groups which are in some way simply related to each other. Get familiar with them a little bit and what they can do before we try to write down the whole damn standard model of particle physics, which is a monstrosity. I mean, you know, it's not my fault, certainly not my fault, that the standard model of elementary particle physics is an ugly, monstrous mess. It's not Steve Weinberg's fault. It's nobody's fault, or if it is somebody's fault, that person, well, he may be in the room, but he's a little bit diffuse. Frankly, we don't understand why the particles are what they are. We don't understand why there is an electron and no particle whose name slips my mind because nobody's ever named it because it doesn't exist, but nevertheless, why some particles exist and why other kinds of particles don't exist, we largely, by and large, don't know. We do understand some relationships between particles. If this one and that one and that one exist, then there's got to be another one to match up with them in some appropriate way. But in the end of the day, there are many more parameters, many more different types of particles than there are known relationships between them which cut down the size of the problem. Okay, the mathematics and the relationships cut down the size of the problem somewhat, factor of 2, factor of 3, or something like that, but there are hundreds of particles. So it is honestly a mess. If you want to understand what people are hoping for in the next round of experiments and so forth, you have to understand some of that mess and what the puzzles are about it. So let's begin. Let's name the particles. We begin with the most obvious ones. Let's make a table. Let's see, we need some columns. We can put the name of the particle over here. I'll put the symbol for the particle over here. I'll put the particle type over here. Now, what do I mean by type? I simply mean whether it's a fermion or boson. I'll put the electric charge over here. There's another quantity which characterizes particles. We'll call it the baryon number. I'll tell you what it is as we go along. And there are other properties. At the moment, I'm not listing them. And we'll put the mass over here. All right. The first one, of course, and I'm not listing them in any particular order. As it happens, I am writing down the lightest one first. The lightest one is, of course, the photon. The standard symbol for a photon is a gamma, like for a gamma ray. It has a field associated with it. The gamma particle is the quantum of a field. In most cases, or many cases, the field carries the same symbol as the particle itself. But for the photon, the field is called A, and it's really the vector potential of the electromagnetic field. You could use electric or magnetic fields, but you can also use the vector potential, which is another way of describing the electromagnetic field. It's a boson. I didn't write down the spin, but the spin is 1 unit of spin. The electric charge is 0. The baryon number, whatever that is 0, and the mass is 0. So that's the first particle. Next particle of interest is the electron. Now, the electron is a particle which has an antiparticle. It has an electric charge. If it has an electric charge, it must have an antiparticle of the opposite charge. And it is a convention whether we think of the particle as the electron and the antiparticle as the positron, or whether we think of the positron as the particle and the electron as the antiparticle. The relation between them is mutual. All right, so when I write the electron, I really mean the electron and positron. And so we could write E here plus minus. Standing, E minus is the electron, E plus is the positron. The field of the electron is usually psi, and maybe you could put a little e downstairs to indicate that it stands for the electron. It's made up out of creation and annihilation operators for electrons. Electrons are fermions. Its charge, okay, its charge in what units now? Well, the standard particle physics or quantum mechanical unit for electric charge, believe it or not, is the electric charge of an electron. It's a good unit to work in terms of. You can go look it up in coulombs. It's 10 to the minus, 23 10 to the minus 19th coulombs or whatever. Yeah, it's some very small charge. But it's not useful to think about it in coulombs. All particles in nature have electric charges which are integer multiples of the electron charge. This is not true of quarks, but quarks are not observable particles. All right, so the charge we'll just write as -1 for the electron and +1 for the positron. Right. So since we typically think of the electron as the particle and the positron as the antiparticle, let's just call it -1, and remember that the positron has the opposite charge. Baryon number is 0, and its mass. Now we have to decide on units for mass. Okay? Units for mass are the same as units for energy. E equals mc squared, so we can either describe the mass as a mass in kilograms or an energy in joules, or we can simply invent a new unit which is more appropriate to microscopic physics, to atomic physics. In fact, the unit that we use comes originally historically out of atomic physics. It is the unit in which the ionization energy of an electron in a hydrogen atom is what? 13.5 electron volts. An electron volt is how much energy you get if you pass an electron across a capacitor plate of 1 volt. It's a very, very small amount of energy, some tiny fraction of a joule. But 1 electron volt is the standard unit that came historically out of atomic physics, the theory of electrons and so forth. It's going to wind up being too small a unit for us. Particle physics energies are larger than atomic physics energies, but for historical reasons, we have the electron volt is our unit of energy. And the mass of an electron measured in electron volts is of order 1,000,000 electron volts, 1 MeV. In fact, it's a half an electron volt. Not exactly. I think it's 0.51 MeV, and MeV stands for millions of electron volts. An MeV will be too small a unit for many other purposes. As I said, the particle physics is a mess, and the masses of particles extend all over the map. And so in trying to search for a useful unit, you're always frustrated. The useful unit will always be too small for the next... Shouldn't it be exactly a half? No, why? No, it's exactly 0.51. No, it's not. What's that? Pi 3. Pi equals 3. No, right. Okay, now we can start. Quantum electrodynamics is the theory of electrons and photons, and we've talked about it a little bit, more than a little bit. And we could also write down over here a table of the various. We won't make it a table. We'll just draw some pictures. The basic elementary process that takes place in quantum electrodynamics, photons and electrons, is the emission of a photon by an electron. electron, electron, photon. And as I've showed you several times, you can rearrange the legs of this diagram so that this could represent not the emission of a photon, but the absorption of a photon. A photon comes in from the past, or, whoops, sorry, you can even flip the electron legs around so that it looks like this. Electron going backward in time. Well, what does that mean? That really means a positron emitting a photon. So the basic building block for building up processes and interactions is this vertex with two electrons, electron, positron, whatever, coming, one going in, one going out, and a photon coming out of it or going into it. Out of that, you build up all of the various processes of quantum electrodynamics, but in particular, the process or the phenomena that corresponds to the force between charges. And in the language of particle exchange, it's the photon bouncing back and forth between charged particles, which creates that force. Yet another way to describe what's going on here is in terms of a Lagrangian or a term in a Lagrangian. The Lagrangian describing this process here describes one electron in, one electron out, and one photon out. And so you build that out of the field operators. One electron in is psi electron. It has the creation and annihilation operators in it. An electron out is psi dagger of the electron, and a photon emitted is the field operator for the photon. And if you plug in all the creation and annihilation operators, you will find in here, buried in here, terms where a photon is emitted, an electron absorbed, another electron emitted, and so forth. And this codifies, this describes all of the various basic processes that can happen in quantum electrodynamics. Now, there's a parameter in the Lagrangian appears the electric charge of the electron, and that, roughly speaking, is associated with the amplitude for an electron to emit a photon. An electron, let's say you hit the electron or whatever, the electron plows into the side of a X-ray machine. What's the probability that a photon will be emitted? Well, the amplitude is the electric charge, and the probability is proportional to the square of the electric charge. So all of this here is a way of describing all of these basic processes. And when they're combined together, they produce forces. They produce processes where photons are emitted. The whole world of quantum electrodynamics flows out of this basically one expression here. We won't try to go through that again now. But let's start adding a little bit to our particle list. The next particles of interest, these are of course familiar to you, I'm sure. Right? Now, if this were 1960, well, I was 1962 when I went to graduate school, probably the next particles I might write down would be protons and neutrons. Protons and neutrons are now subsumed by quarks. It is widely believed that in some sense protons and neutrons are composites of quarks, although we will remind me to come back to this issue of the difference or what it means to be composite versus elementary. It's a very interesting story. But naively, quarks are smaller than protons and neutrons, and so protons and neutrons, which are big fat globs, are made up out of quarks. Okay. So next thing are quarks. There's a lot of quarks. We won't even get to all of them tonight, or the whole set of distinctions between them. I don't think we will. But there's more than one type of quark. There are 6 types of quarks, 6 distinct particles, all of which are very similar to each other in some respects, very different from each other in other respects. So let's list them. There are They go under, they have names, all right? Well, why are they called what they are? They're called what they are, just historically, randomly, people assigned silly names to them. And there's no logic to what they're called, no logic at all. There's first of all the up quark, and that's called U. The symbol is U. Well, let's see, we should write there are quarks here, quarks. And I suppose the symbol for quarks is Q. Right? All quarks are fermions. We'll write down their charge later. They have all baryon number of 1/3. Now, why 1/3? Well, the reason is very simple. The baryon number is basically the counting of the number of protons and neutrons. Each proton is counted as having 1 unit of baryon number. Each neutron is counted as having 1 unit of baryon is just a word for protons and neutrons, and a somewhat generalization of protons and neutrons. Nucleon is a word for protons and neutrons. There are other particles, which we'll come to, which are very similar to protons and neutrons. They're also called baryons. The prefix bary, I think, means heavy. And baryons were called baryons because they're a lot heavier than electrons. But counting up the number of protons and neutrons, what do you call the number of protons plus neutrons in an atom? The atomic weight, yeah. The atomic weight, yeah. The atomic weight is equal, approximately equal to the total number of protons and neutrons. And the total number of protons and neutrons in nuclear physics never changes. Protons can turn into neutrons. Neutrons can turn into protons plus other things. But the number of protons plus neutrons never changes. And you do have isotopes. But still, the number of protons plus neutrons doesn't change. Number of protons can change. How can a number of protons change? Oh, yeah, indeed they do. But are there processes where the number of protons and neutrons change? Protons, not plus neutrons, but protons and or neutrons change? Beta decay, radioactivity. In radioactivity, one form of radioactivity, a neutron decays into a proton plus an electron and an antineutrino. Okay, so in that process, the number of protons changes by 1, the number of neutrons changes by 1, but the number of protons plus neutrons doesn't change. There's a generalization of that in all of nuclear physics and particle physics. There's a certain quantity which, for ordinary nuclear physics, is just the number of protons plus neutrons, and that number is sometimes called the baryon number. We'll have to generalize it a little bit beyond protons and neutrons. It's the baryon number. And it could have been defined to be 2 for the proton, or 7 for the proton, or pi for the proton. But whatever it is, it has to be defined as twice as much for 2 protons, 3 times as much for 3 protons. So it's a convention that you say the baryon number of the proton is 1. Incidentally, what's the baryon number of the antiproton? -1. -1. Proton has baryon number +1. Antiproton, baryon number -1. Neutron, baryon number 1. Antineutron, baryon number -1. But clearly there's an element of convention in exactly what you call them. But once it was fixed that the baryon number of a proton was 1, then the baryon number of a quark was 1/3 because 3 quarks make a proton. Okay. So it's just a historical glitch that the baryon number of the most fundamental thing in nuclear physics is 1/3 and not 1. What about an antiquark? There are antiquarks. Baryon number is -1/3. All right? So I won't write that down separately.
The number of quarks is conserved?
Number of quarks minus the number of antiquarks is conserved. Now, whether or not that is an absolute conservation law, it is not believed to be an absolute conservation law. What do I mean by absolute conservation law? Can a proton disappear? It can't completely disappear. Its energy has to go someplace. Are there processes in nature where a proton might disappear and become something that is neither a proton nor a neutron or anything else that you would call a baryon. For example, without violating charge conservation, a proton could become a positron and a photon. So a proton could decay into a positron and a photon. Does it? Well, you can wait, if you have a single proton and you sit there and wait, you will wait a long, long time before that proton decays. Its half-life to decay that way is at least 10 to the 33 or 10 to the 34 years. So this is not something that happens very regularly. Does it happen at all? The thinking is yes, it does, but this is one of the very, very interesting questions of particle physics of whether the proton can decay. And when you say can it decay, you mean decay into something that does not carry a baryon number. And it is widely believed that the answer is yes, but it has never been demonstrated. Incidentally, how do you wait around for 10 to the 34 years for a proton to decay? You get 10 to the 34 protons, and you wait around for one of them, and you have to see one. Now, 10 to the 34 protons is a lot of protons.
If you have protons and antiprotons,
No, that's not that. That's zero baryon number because it goes to zero baryon number. A proton has baryon number 1. An antiproton has baryon number -1. So that's not a baryon. We call them baryon-violating processes, processes in which the baryon number is not conserved. Nobody has ever witnessed such a process in the laboratory or anyplace else. Can they happen? There does not seem to be any reason why they cannot happen built into the mathematics of what we know. So we leave this as an open question, but empirically, and at least to a very, very high precision, baryon number is conserved, and quarks, by definition, have 1/3 of a unit. 1/3 of a unit. As I said, -1/3 for antiquarks. But in order to fill in the rest of this, in particular, electric charge and mass, we have to label which kind of quark we're talking about. And there are lots of different kinds of quarks. So let's put in the list of different kinds of quarks. This is not new particles which are not quarks. This is just a subheading here, quarks and then things underneath. There are up quarks, down quarks. Why are they up and down? They're not up and down. There's nothing up and down about them. What directions? Up and down? Up and down means in the Earth's gravitational field. There's nothing uppy or downy about them. All right? Then it gets worse. There are strange quarks, which are no stranger than non-strange quarks. All right? It gets more silly. There are charm quarks, which are charming, I suppose. I don't know. And then there are, now this is, if you don't, you know, if you're squeamish or, you know, very, there are bottom quarks, and then top quarks. And the symbols are, of course, exactly the same. I just didn't feel like writing the words. Up, down, strange, charm, bottom, top.
wasn't there beauty and truth?
Same as bottom and top. I got a little pretentious beauty and truth, so bottom and top. Strange and charm. How and under what circumstances these things were named is not interesting. I don't know. I do know, but never mind. They're all fermions. Okay, the symbols are just what I wrote here. They're all
What's the field symbol?
Sometimes Q, sometimes psi Q, sometimes capital Q. Sometimes, depending if you're talking about the individual types of them, you'll just use U, D, S, C, B, or T. Use the same names for the fields as you use for the particles. And there's no completely coherent convention that everybody sticks to. All right, they're all fermions. The whole lot of them are fermions, as I said. But now comes the charges. So it's useful to divide them into groups of 2. These groups of 2 are sort of repetitions of each other. This group of two, in many ways, is isomorphic, not exactly, to this group of two, which is the same as, not the same, but which follows the same pattern. The pattern of these two is similar to the pattern of these two. Is similar. Oh, I got them upside down. Excuse me. Wait. If I want to keep the pattern, let me see. I think I want to put down, up. Down, up, strange, down, up, strange, charm, bottom, top. Yeah. All right. So the down-up system is very similar to the strange charm system, is very similar to the bottom-top system. So let's write down what the electric charges are, and you can see them. You can see this similarity. The down-up system has charge minus 1/3 and 2/3. That's the first example of particles in nature which have charges which are not integer multiples of the electric charge of the electron. Okay? However, quarks by themselves do not exist freely in nature. They're always bound into other structures, protons, neutrons, and so forth, and those particles do have integer charges. Okay, the strange and the charm, exactly the same thing, minus 1/3 and 2/3. Bottom and top, exactly the same, minus 1/3 and 2/3. Can that be read? They're just repetitions of the same thing. What about the antiparticles? If I were to list the antiparticles over here, they would just have exactly the same charges as the particles, except opposite sign. Okay. So this is simply replication for some reason that nobody understands. Nobody even has any idea why nature replicated itself this way.
Are they still all baryon number 1/3?
Yeah. They're all baryon number 1/3. Right. Okay, and then the masses are not similar to each other. The masses wildly vary. I'm going to put down estimates for them because the precise value, well, there are precise values of the masses, but you can go look them up on Google or wherever you want. The down quark is about 10 MeV. So it's 50 times heavier than the electron, a lot lighter than the proton. Incidentally, what's the proton mass? About 1,800 times the electron mass. In other words, about 940 MeV. This is a lot lighter than a proton. The up quark, about 5 MeV, less than the down quark. And protons are made only out of up quarks and down quarks. So it doesn't look like there's nearly enough mass in quarks to be the mass of a proton or neutron. Okay, we'll come back to that. The point is, of course, there's more in a proton than just its quarks. Okay, strange and charm. Strange is roughly order of magnitude 100 MeV. That's strange. And charm is a little over about 1,000 MeV. Now notice that the down quark is heavier than the up quark, but the strange quark, which is analogous to the down quark, is lighter than the charm quark. So there's some pattern of inversion here of the masses. Again, nobody understands at all why that's true. Yeah, charm is about 1,000, 12, a little more than that.
You wrote down 100. The right-hand side.
Ooh, sorry. 100, missed the 0. Decimal creep. Okay, 1,000 MeV. And the bottom quark is about 5,000. Oh, this is called a GeV, giga electron volt. The bottom quark, see, we keep changing units. That's about 5 GeV. And the top quark is about 170 GeV. So how much heavier is the top quark than the up quark? Can anybody do that calculation? How much? 30,000? A lot. A lot. All right. So on the one hand, these particles are extremely similar to each other. They do the same things, they have the same properties, and yet they have masses which wander all over the map. Does anybody understand why? No. Are there any ideas? Yes. Do any of them work? No. We don't even have a clue about why there's, first of all, we don't even understand, of course, why there's even one of them. One family, these are called families. Why is there one family? Well, we don't know, but for sure, if there wasn't one family, we wouldn't be here because there would be no protons and neutrons. But given that there's this one family of up quarks and down quarks, why are there strange quarks and charm quarks, or top quarks and bottom quarks? Nobody has a clue.
Another stupid question.
Yeah.
When these quarks were found, the story goes that they were looking in a certain place because the math said the mass should be a certain amount. In other words, they said that when they went through the calculations and they knew that this is where it was going to be, that it was going to be somewhere around so many GeV that they were going to find.
Oh, the top quark in particular.
Yeah, in other words, they predicted that it would be there before they went and looked for it.
Yeah, but not on the basis of, abstract theory, but on the basis of how the top quark would affect work its way into other particles' properties. And,
well, I was just saying because you just said that the numbers, nobody knows why, and they're all over the ballpark, but yet they seem to know that that's where they wanted to look for it.
Yeah, but not because there was any basic underlying reason why the top quark had that mass. What you could do is you could say, supposing the top quark had a certain mass, and then calculate various Feynman diagrams involving the top quark in various ways. Feynman diagrams involving ordinary particles, not the top quark, but which had top quarks running around in the interior of diagrams. Okay? You calculate those diagrams. Those diagrams have an effect on processes involving other particles that you know very well. And then you say, what does the mass of this top quark have to be in order that it does the right thing for these other particles, right? So it was not in any sense a deep understanding of why the mass of the top quark was what it was. It was simply an observation that you needed that particular value of the top quark mass in order that it be consistent with, yeah, right.
So you can't observe a quark, but you can predict how it will disappear. What will happen if there is one? What kind of showers and directions and energies of particles will be observed?
Go ahead. You're asking or you're saying? To say that you can't detect a quark becomes, to a certain extent, a matter of definition. What it means to detect a quark. You can certainly detect evidence of quarks. What you can't do is create an isolated quark in isolation from other things and then examine it. But we're going to come to the question. I think you're probably remarking about jets produced. Well, I don't know what you're talking. Yeah, we can talk about jets. Let's come back to it after we've talked more about quarks. Yeah.
Does the fact that some quarks have twice the charge in absolute values as others, is that from the theory, or is that just the bookkeeping kind of?
Semi-theory, yeah, to some extent that is understood. I'm not going to explain it now, but now I'm telling you the facts. We can talk about how much of this is explained and how much of the pattern is. The right question is how much of this pattern is required for theoretical mathematical consistency. But we haven't gotten there yet. Some of this pattern is required, yeah. Some of this pattern is required, but not much of it. Very little of it is required by mathematical consistency.
Question?
No.
Is the relative abundance of the 6 kinds of quarks
Relative abundance in where? Well, what do you mean by relative abundance? You mean in the world?
in the universe, yeah.
Neutrons are unstable, they decay. Protons are stable, they exist in intergalactic space and everything else. They're all, oh yeah, the only thing that has any appreciable abundance, all right, first of all, the only quarks which have any degree of stability are ups and downs. The rest of these decay to these. So the real abundance of real particles in the universe are all ups and downs. Okay? Now, what's the relative abundance of ups and downs? That's determined by how many quarks of each type there are in a proton. There are no neutrons. Oh, sorry, of course there are neutrons. There are neutrons in atoms, in nuclei. So you have to know the relative abundance of protons and neutrons to know the relative abundance of it. But that's all it is, relative abundance of protons and neutrons. Okay, so what do we know? What is a proton and what is a neutron in this language? And let's come over here. A proton is 3 quarks, and a neutron is 3 quarks. Now, as I said, I'm now in the business of telling you facts about these particles, not at this point trying to understand why these are the facts. We can't do everything at once. A neutron is 2 down quarks and an up quark. Let's just check that. An up quark has charge 2/3, and a down quark has charge -1/3. So 2/3 minus 1/3 minus another third, this is electrically neutral. Charge equals 0. That's good. Neutron has charge 0. Proton. Proton is exactly the same as a neutron, except with an interchange of up quarks and down quarks. 2 up quarks and a down quark. Okay. Now, up quarks and down quarks are a lot alike, except for their electric charge. The electric charge has to do with the interaction with photons. Let's forget photons. Let's forget about the existence of photons for the moment and just talk about quarks and the other particles which are important inside the nucleus and so forth. Then it would almost seem that a neutron and a proton are the same thing except for an interchange of the up label and the down label. You might then surmise that their properties are almost exactly the same if for some reason the electric charge is unimportant. In other words, supposing we don't have to worry about the interaction with photons, just forget photons, then it would seem that protons and neutrons should be identical, because what's the difference? You just replaced up quarks by down quarks. But it's not quite true, because up quarks and down quarks don't have exactly the same mass. Right? They don't have exactly the same mass. Now, 10 MeV, by comparison with the mass of a proton, is small. It's almost negligible. It is very small, and it's almost negligible in nuclear physics or in particle physics. And so to some precision, to the extent that you can ignore the masses of the quarks, which are, after all, smaller by far than the masses of protons and neutrons, neutrons and protons are a good deal alike. Right? The only difference is the slight difference in mass between the up quarks and the down quarks. Which one is going to be heavier, the neutron or the proton? And of course, it's going to be the one with more down quarks, because down quarks are a bit heavier than up quarks. Down quarks are a bit heavier than up quarks, and so it's likely that the neutron is heavier than the proton, and it is. Okay? Neutron is a little bit heavier than the proton, and it's largely attributed to the fact that the neutron has more down quarks. Now, that's not all there is to the difference between protons and neutrons. If the down quarks and the up quarks had exactly the same mass, but you accounted for electromagnetism, in other words, the photon. You said, okay, the photon is not completely unimportant. Then which would be heavier, the proton or the neutron? Why? Yes, because it has some electrostatic self-energy because it's charged. Okay? So the proton would be a little bit heavier because of the self-energy of the electromagnetic field, the electric field. One would expect the proton to be a little bit heavier. In fact, the neutron is a little bit heavier, and the reason is because the down quark is a little bit heavier than the up quark. Okay, but other than that...
You going to give us the masses?
Of which?
Neutrons and protons.
Yeah, a neutron is about, what, 938 MeV, and proton is about 939 MeV, or... what was it, about 1.4 MeV difference between them? Something like about 1.4 MeV difference between them. There's enough energy between them, there's enough energy separating them, that the neutron can afford a little bit of energy to, when it decays into a proton plus an electron plus a neutrino. There's a little bit of excess energy in the neutrino which allows it to decay. And allows it in particular to decay with an electron, to an electron. Okay, so that's the very, very rough story of protons and neutrons. We'll come back to it. But now there are also these strange quarks. Let's forget charm quarks for a moment. There's an interesting question. Can you replace, now notice that in every respect, the down quarks and the strange quarks are similar to each other, except for the fact that the mass is different. So you might ask, can you construct an analog of the proton and neutron where you pull out a down quark and replace it by a strange quark? Or perhaps two strange quarks. Pull out a down quark and replace it by a strange quark. The answer is yes, of course you can, because in every respect the up quarks and the down quarks are the same. It's sort of almost like an isotope. You pull out a proton and put it in a neutron and it sort of sticks together sort of the same way, but it's even better here. So you can construct another kind of analog. These are called strange baryons. Strange baryons, I forget their names, lambdas and xi's. They've got all kinds of names, and you know, it's been so long since I worked on these things that I can't even remember their names. They have symbols like this associated with them, like this, and lambdas. I don't remember which one is which, not important. But for example, you can create, I don't know what its name is, pull out a down quark and create a strange and a down and an up. What's the mass of this one over here? Sorry, not the mass. What is the charge of this one? Well, it's exactly the same as a neutron because you pulled out a down and put in an S, and the S and the down have the same charge. All right, so this is also electrically neutral, but it has a strange quark in it, and it's called a strange baryon. Okay? They're not stable. They can decay. We're going to discuss the decay processes later, but they're not completely stable, so they evaporate, and this one will turn into that one. But yes, they do exist. Likewise, you can put in two strange quarks and an up quark. What is the charge of that one? Same thing. Charge neutral again. And likewise for the proton, you can replace it by up, up, and strange. So there are all these strange baryons.
When
They
they
exist.
decay, when those decay, what kind of products do you get?
What kind of what?
Products do you get?
Oh, protons and neutrons.
Only protons and neutrons?
Yeah, well, no. You get some proton pions and other things, but electrons and other things. Of course, you can't just get protons. You have to get some energy out.
And you also only substituted stranges for downs,
Yeah.
and not ups or...
No, you can't. No, this. Well, the rules of what you can exchange are a little bit complicated, but at the moment, you can always exchange one for a similar one of the same charge. All right? Now, you can also, oh, incidentally, these strange particles are a little bit heavier than the protons and neutrons because of this extra 90 MeV of, an extra 90 MeV. 90 MeV isn't much. All right? So they're somewhat heavier than the ordinary protons and neutrons. But in every respect, they're similar. The main difference of importance is because they're heavier, they can decay to the protons and neutrons, and so they're not found in the universe in any abundance.
All of those that you put up there so far can be constructed with antiquarks also.
Oh, yes. Yeah, you'll have to take every particle and replace it by its antiparticle. Then it becomes the antineutron, the antiproton, and the anti-question mark.
You call these strange baritons.
The strangeness is just another word for saying they have a strange quark.
But if you put a bottom quark in?
Okay, then they become bottom.
Then they're bottom baritons.
Then they're bottom baryons.
Strange baritons is if you put an S in.
Yeah, yeah, yeah. Strange. Are they strange? Well, I don't know. I mean, they were called strange because people became familiar with protons and neutrons by the 1950s, and then when they discovered these other things, they said, "Oh, that's strange," and the unexpected things. Yeah.
Where's the missing mass come from the proton and neutron?
Yeah. Missing mass between, what do you mean missing?
Well, if you have the mass of the...
Oh, you mean if you just added up the mass of the quarks. Right. Yeah. That's right. There's a lot missing. So there must be something else in the proton and neutron. No, they're gluons. Yeah. No attempt here to be dramatic. But the gluons don't carry any interesting charge, baryon number. Do they carry mass? Well, they carry energy. So
back to what you were saying there, it's binding energy.
it's a form of binding energy, yeah. That's right, it's binding energy. Energies don't add. Not relativistically. I mean, well, masses don't add. The mass of an object is not necessarily the mass of its constituents.
Well, it's what you were saying about the covalent bond type thing.
Right.
You're using the language of particles here to describe these composite particles. It seems more complicated if you use the word language of fields. Like, how would you combine a down field and up field? It seems like you would combine everywhere and not be a particle.
Say it again.
A field.
Do you want to know whether you can construct a field describing a proton?
Yeah, you're using down and up as if they're particles.
Yeah.
But if you think of them as fields, then they're everywhere, and your modes of the field are combining to form these composite particles.
Well, in thinking about this particular aspect of things, it's much easier to think about particles than fields. We could think about it in terms of fields, but it's much harder. And
question about the binding energies.
Yeah.
So if this difference between the quark energies and the proton energy or binding energy, that's a big positive energy. And
no, it's not an integer. It's not an integer.
No, it's a big positive energy.
Energy. Oh, I thought you said integer. Yeah.
And usually when you think of things being bound,
Usually negative. Right. Right. Not true here. Okay, so. Well, yeah. I mean, we'll come to it, but yeah, sure. Yes. Yes. Let's. Yes, there is. Yes, there is, but not yet. Let's talk first about mesons. Mesons are simply quark, antiquark. Now, why? You could raise the question. Why do 3 quarks bind together to form something? Why don't 2 quarks bind together to form something? Okay. In the early days of quarkology, this was a complete mystery. Why quarks always, you could say, oh, it's in order to make the charge an integer multiple of the electron. Well, that's a stupid answer. And turned out not to be that stupid, but at this stage, it's a stupid answer. But yet, that is the pattern. That is the pattern, that they combine together in forms in which, this is not the only rule, but this is one of the rules of nature. We do understand it, and we do understand where it comes from, but a rule of thumb at the present time, is the way things bind. They always bind into combinations which have integer multiple of the electron charge. Okay, so you can take that as a working rule temporarily until we have a deeper understanding of it. All right, mesons are also particles, composite particles, which also have the property that their charge is integer multiple of the electron charge, but they have 0 baryon number. They do not have baryon number, which means that they must be made, that they're combinations of quarks. They must be made of quarks and antiquarks. In fact, they are quarks, a quark and an antiquark. They're a quark and an antiquark, and so let's write down. There are, first of all, the ones that you can make only out of ups and down quarks. Ups and down quarks are special, not in any deep sense, but they're special because they're much lighter than the other particles. They don't decay, or they don't decay as rapidly if they do decay. They're abundant in nature, and more than that, it doesn't take any energy, it doesn't take much energy in collisions to make them. So of course they were the first particles to be discovered, things made up of only up quarks and down quarks. The up quarks and down quarks are pretty light, and the mesons are typically pretty light. They're an up quark and a down quark, and a quark and an antiquark. And then you can start thinking about the different combinations. Okay. There's an up bar quark and a down quark. There's an up quark and a down bar quark. There's an up bar and an up quark, and there's a down bar and a down quark. I think I got them all.
Question?
Yeah.
Any quarks have the opposite spin? Any quarks have the opposite spin?
No, you can't do that. Don't they have to be the opposite kind because it's 1/3 and 2/3? So it's got to be.
No. Okay, let's work out what their electric charges are. The electric charge of an up quark is -2/3, and this one is -1/3. So this has charge -1, right? -1/3, -2/3. All right, that's fine. Charge -1 is like an electron.
Oh, you're right.
All right. What about this one? This is the antiparticle of this.
Those are going to be 0.
This one's not. This one is just the antiparticle of this.
The ones that I was worried about.
Oh yes, right. This one is these two are antiparticles of each other because they are related by changing particles into antiparticles. Down bar into down, up bar into up, and this has charge +1. Right. So these are antiparticles of each other. Up bar up, that's electrically neutral, obviously, and charge equals 0. Now, in fact, neither one of these two by themselves correspond to distinct particles. Remember, we're doing quantum mechanics. Each one of these states can be thought of as a quantum state. Think of it as a quantum state. The quantum state consisting of an anti-up quark and an up quark. The quantum state consisting of an anti-down quark and a down quark. One of the things you can do in quantum mechanics is to superpose states. If you have states, you can add them. You can superpose them. Superposing them means making combinations that have a probability for being either this one or this one. Right? There are two combinations of these two, and I'll tell you what they are. They are up bar up plus down bar down. And what would I put in front of it to make it have total probability 1? 1 over square root of 2. This is a quantum state, and this is the orthogonal quantum state. Up, bar up, minus down bar down. You know what this is? This is an entangled pair of quarks. Not entangled through their spin, but entangled through their upness or downness. If you thought of upness and downness as like being similar, analogous to the spin direction of a particle, up or down, and that's where this terminology came from, then these would be two entangled states, entangled not through their spin, but through their isospin, through their upness and downness. We haven't used the word isospin. Maybe I'll tell you what it means, but not right now. It is just this analogy between the spin directions and the upness or downness quantum number. These two things individually are well-defined particles. This one over here goes together with these two, and they are called the pions. They go together for a good reason, for a good mathematical reason, but they go together, do I have the right ones? Yeah, they go together because their mass is very close to each other. It is believed they would be exactly the same mass if the up quark and down quark had the same exact mass, if the masses were the same. All three of these are virtually indistinguishable except for a small difference in their mass, and they have different charges, 0, +1, and -1, and this is called the pion multiplet, pi, plus, minus, and 0. 3 independent kinds of particles called pions, and as I said, and we can discuss why nature chose these particular combinations to be analogous to each other, but now I'm telling you facts and not mathematics. And the other combination is simply this one over here, and this is called the eta. So there's the pi plus, the 4 states here really define the 3 pions, pi plus, minus, and 0, and the eta meson. The eta meson is similar to a pion in many ways, but it's heavier. Why is it heavier? That is a complicated story. It's not an elementary story. It's a complicated story. Maybe we will come to it, maybe we won't. But as a matter of fact, its mass, okay, what are the masses of the pions? The masses of the pions are about 140 MeV. The mass of a pion, M pi, is about 140 MeV. So in other words, it's not too different from, question? Yeah, it's about 140 MeV. So it's somewhere in this range in here, not this heavy. And the mass of the eta is about 3 times heavier or something like that. The mass of the eta is about 500 MeV. I don't remember the precise number, but that's about right. Why that is, why the eta sticks out as being different, was a puzzle for a long time. It's not obvious. Not obvious. Even today, it's a rather abstract mathematical fact, but it is understood.
Isn't it also true that they're relatively long half-lives?
Not very long.
I mean, compared to most of them, they're like numbers of orders of magnitude different.
They don't decay by strong interactions. They decay by weak and electromagnetic interactions. So they're longer lived than many of these other particles. Yes, that is true. Right, they are long lived. Okay, those are the mesons.
Did you give a name to the up bar, down bar?
Yeah, those are pi.
No, they don't have names by themselves. The linear combination, which are the sum and differences of them, have definite names.
Oh, I see. Yes, those are.
Is that similar to Is that something like the neutrino oscillations?
Well, in the sense that it's related to quantum superpositions of states, yes, but it's got more to do with spin combinations of two half-spin particles. There are two ways that you can entangle. Well, we'll come to it next time. The last thing I simply want to tell you is that you can make strange mesons. You can take any d quark and replace it by a strange quark, strange bar quark, and so forth. That makes new mesons, which are called strange mesons, or what's the other name for them? K-mesons. K-mesons are mesons containing a strange or an anti-strange quark, replacing a down quark. Okay? There are 4 of them. Up bar strange, up strange bar, down bar strange, down strange bar. These two have charge 0. Charge 0. And these have charge +1 and -1. These two are called the charged K-mesons. These two are called the neutral the neutral K-mesons. So there are 3 kinds of pions, 1 kind of eta, and 4 kinds of, how many does that make altogether? Let's see. 3 pions, 4 K-mesons, and an eta. Yeah. 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 There's more. There's more. There's more. Oh, did we leave something out? Yeah, we left out one. We left out some. We left out S bar S, huh? Yeah, there's 9. Right. Right. 9 altogether. The reason it's 9 is simple. There are 3 kinds of quarks, 3 kinds of anti-quarks. 3 times 3 is 9. Yeah. Right. Okay.
For more, please visit us at stanford.edu.